So today we'll be discussing the dynamics of rotational motion, particularly about torque and angular acceleration for a rigid body, and angular momentum. A machinist is using a wrench to loosen a knot. The wrench is 25 centimeters long and he exerts a 17 Newton force at the end of the handle at 37 degrees with the handle. So what torque does the machinist exert about the center of the knot? And what is the maximum torque he could exert with the force? And how should the force be oriented? So in solving the torque, we use the equation torque equals radius times force times sine theta. So first you have to convert the radius from centimeters to meters. And then you substitute the value into the equation, you get a torque of 2.56 Newton meter. Then second, the machinist could exert the maximum torque when the force is applied at the end of the wrench at an angle of 90 degrees. So again, you use the equation of radius times force times sine theta. And then you plug in the values, but this time, for the theta, you put 90 degrees and you'll get 4.25 newtons meter for the torque. This problem is about torque and angular acceleration for a rigid body. A uniform disc with mass of 40 kilograms and radius of 0.2 meters is pivoted at the center about a horizontal frictionless axle that is stationary. So the disc is initially at rest and a constant force of 30 newtons is applied tangent to the rim of the disc. So what is the magnitude V for the tangential velocity of a point on the rim of the disc after the disc has turned through 0.2 revolution? And what is the magnitude A of a resultant acceleration for a point on the rim of the disk after the disk has turned through 0.2 revolution? So first, we can find the angular acceleration using the formula for torque, which is inertia times acceleration. And then we isolate acceleration, and it will be equal to torque over inertia. So torque can also be equal to radius times force, and inertia can also be equal to 1/2 times mass times radius squared. And then we cancel the radius on the numerator and only r will be remain at the denominator. And then we plug in the given values in the equation, which is acceleration equals 2 times f over mass times radius. And we will be obtaining 7.50 rad per second squared for the acceleration. And then now we can find the angular velocity after the disk turns through 0.2 revolution. We will be getting the angular velocity using the formula final angular velocity squared equals to initial angular velocity squared plus 2 times acceleration times theta. So now we will remove the initial angular velocity since it's initially at rest, and then we we put we substitute the value in the equation, which is angular velocity equals square root of 2 times acceleration times theta, and we will be obtaining 4.34 rad per second for the angular velocity. So now we can use the angular velocity to find the tangential velocity. We will use the equation of tangential velocity equals angular velocity times radius. So the angular velocity that we obtained was 4.34 rad per second, and we multiply this to the radius, which is 0.2 meters, and we will be getting the tangential velocity, which is 0.868 meters per second. So now we'll be getting the magnitude of the resultant acceleration, but first we have to find the tangential acceleration. So we'll be using the equation tangential acceleration equals to the constant acceleration times radius. So the constant acceleration is 0.50 rad per second squared, and then the radius is 0.2 meters. And we substitute that to the equation, and we will be getting a tangential acceleration of 1.50 meters per second. So using the tangential acceleration, we will be getting the centripetal acceleration. So the equation for centripetal acceleration is angular velocity squared times radius. So now we plug in the values in the equation, we will be getting 3.77 meters per second squared. So using the centripetal acceleration and tangential acceleration, we can now find the resultant acceleration using the Pythagorean theorem. So substituting the value to the equation of resultant acceleration equals square root of tangential acceleration squared plus centripetal acceleration squared, we will be getting 4.06 meters per second squared. So this last item is about angular momentum. So a woman with a mass of 55 kilograms is standing on the rim of a large disk that is rotating at 0.47 revolution per second, about an axis to its center. The disk has mass of 119 kilograms and a radius of 3.5 meters. So now we calculate the magnitude of the total angular momentum of the woman, which is we will be using the disk system. And we assume that we can treat the woman as a point. So first we have to find the moment of inertia of the system, which is the sum of the individual moments. So we'll use the inertia formula. So it's going to be inertia equals 1/2 times the mass of the disk times the radius squared plus the mass of the woman times the radius of the disk. So we will be obtaining 1,403 kilograms per meter squared. So using this inertia, we can now find the angular momentum using the formula of angular momentum equals inertia times angular velocity. So the inertia is equal to 1,403 kilograms per meter times meter squared, and we will be converting the 0.47 revolution per second into rad per second by multiplying the revolution to 2 pi rad. And multiplying all, we will be getting the angular momentum, which is 4.1 times 3 times 10 raised to 3 kilograms meter squared per second.